Okay, so the next type of transformation is a rotation, lesson 4.3. Again, just like our last two lessons, we had translations, we had our reflections, and now we have our rotations. All three are transformations, and more specifically, they're all congruence transformations or rigid motions. So this is the last one of our rigid motions. Now, a rotation is a transformation in which a figure is turned about a fixed point called the center rotation. Rays drawn from the center of rotation to a point and its image form an angle of rotation. A rotation about a point P through an angle of x degrees maps every point Q in the plane to a point Q prime so that one of the following properties is true. Now, I know that statement was really confusing, and I feel like the way they explain this just is really confusing in the book. However, they have these two figures that almost look like flags. They had the figure with R and Q, and then R prime and Q prime. First thing I want you to note about this figure is they're showing a rotation. It's going 40 degrees. Now, P is our center rotation. They drew these black lines here to show that we are going from Q to Q prime 40 degrees. And the way that they determine it's 40 degrees is they drew these lines to the center rotation and then measured this angle. So we have this angle with these black lines. That's what's 40 degrees. The other thing that's important here about this 40 degrees is the fact that we're going counterclockwise, and this is a positive 40. Whenever we are doing rotations, it is normal to go in a counterclockwise fashion. Most things in math are counterclockwise. For example, when we talk about our quadrants, which there may be questions in this section or this chapter that deal with the quadrants. I might ask you, like, what quadrant did the transformation end up in? Our quadrants in math go counterclockwise. They start in the positive, then go to the negative, then negative, and then positive, negative. So we start in the first quadrant and we rotate counterclockwise. Same thing with this. We're rotating counterclockwise so that all counterclockwise rotations are positive numbers. If we went clockwise and we didn't say that we're going clockwise, then we'd have a negative degree. So a little bit confusing in this. There are positive and negative degrees of rotation. All right. So again, if it's not stated, always go counterclockwise unless otherwise stated. The other important things down here at the bottom, it says if Q is not the center of rotation, P, then QP and Q prime to P. Again, this is really just confusing down here. It's better if you just stick to what I talked about with this figure already. We're going to take a look at an example here in just a second. So let's clear that and go on to the next slide. All right. So here's what I was talking about with the counterclockwise and the clockwise. Whenever we go counterclockwise, again, that's normally going to be a positive degree. If we're going clockwise, it'd be a negative degree, unless it actually states counterclockwise or clockwise. If it says 40 degrees clockwise, then we're going 40 degrees clockwise. If we're going 40 degrees counterclockwise, then you're going counterclockwise. If you say we're doing a rotation of 40 degrees and you don't say what direction, then that's going to be counterclockwise. If you say a rotation of negative 40 degrees, then that's going to be automatically clockwise. So again, a little bit confusing there, but counterclockwise is our positive rotation unless it gives us the direction. All right, on this one, it says draw a 120 degree rotation of triangle ABC around point P. Now, this one, again, they gave us a random point. In order to do this, we'd have to use a protractor. I highly recommend when you do the assignment for this, you use the online textbook. Also, when you use the online textbook, I set up a little bit differently. So try to go to the assignment within Canvas that is labeled as the Big Ideas assignment. It has a BI in front of it. If you go to it, you don't even have to leave Canvas. You can just do the assignment within Canvas on Big Ideas. Again, did a little bit different than I had been doing it. I'm trying different things out. So if you would just try it that way. But on here, draw a 120-degree rotation of A, B, C around point P. So on this one, we actually have to take the original lines. We're going to draw a line from each of those points. So starting with A, we're going to draw a line. Then you would use a protractor to measure an angle going counterclockwise 120 degrees. So we're going to take a protractor, put it on the center of rotation, which was P, and then go 120 degrees and mark that line. Now, we also need to make sure that we make that line the exact same length. So we need to make sure that those two lengths are equal. And then we repeat that with each of the other points. So again, you have to start over, draw a line from B, use a protractor, measure it out 120 degrees, make sure they're equal. Then same thing from C. We're going to take the line from C, again, measure out 120 degrees, make sure that your lengths are equal. And then once you have all 3 points, you can draw your new triangle. Again, are we going to have to do this on an exam? No. Are we going to have to do this on one of our tests? No, I'm not going to make you do this physical rotation. You should be familiar with the steps. You should you should be able to sketch this if I wanted you to sketch it. If I ask you a problem like this on the homework, again, if you're doing it on big ideas, use the tools that they give you. If you're trying to do this on your own paper, I just want you to sketch it. I don't want you to actually use a protractor and all that. So again, it's going to be a little difficult, but please try. All right, on the next one. So now you can rotate a figure more than 180 degrees. The diagram shows counterclockwise rotations of point A at 130, 220, and 310 degrees about the origin. Notice that point A and its images all lie on the same circle. A rotation of 360 degrees maps a figure onto itself. You can use the coordinate rules to find the coordinates of a point after a rotation of 90 degrees, 180 degrees, and 270 degrees about the origin. So these are 3 values that you need to be familiar with, and there's actually rules, which is coming up in another slide. Now, on that figure, again, it's important to notice they are on the same circle because, again, they're always equal distant from that center of rotation. It makes it a lot easier if our rotation is around the origin. And like I said, there's also certain rules that we have to follow if it's the 90, the 180, or the 270 rotation. So here are those rules. When you take a point and you rotate it counterclockwise about the origin, the following is true. So you have point AB. All right, so if we pretend to start off in the first quadrant there, and it's a positive, well, then a 90-degree rotation is going to end up with a negative and a positive. It'll be in the second quadrant, and it'll be reversed. So we are going to switch the X and Y values. So on here, they like using A and B. I like talking about in terms of X and Y. So again, for a 90 degrees rotation, we're switching the X and Y. The original Y value becomes negative. Then for a rotation of 180, they are in the original format, but both values are negative. So both the X and the Y become negatives. And then finally, for a rotation of 270 degrees, you're switching the X and the Y, and the original X value becomes negative. So you can use this rule of thumb when doing any type of rotation of these 3 degrees. Again, if you forget these, you can always draw a diagram. You can start off with a X and Y value in the first quadrant, and then actually take your paper physically. And once you have your paper, just rotate it. So on here, the other thing that you have to note is these are all counterclockwise rotations. If you take your paper and rotate it counterclockwise, you're going to find where that next point is. So again, you could figure these out without having to memorize them, but it's a good thing to memorize them. So just like the rules that we had for the last 2 sections, I'd recommend using a flashcard or an index card, making a flashcard out of this so that you know these rotations really well. because if you're asked for one of these rotations, you should be able to say what it is without having to graph it. All right. The other thing that was mentioned in these past couple slides, 360 degrees, that's a full circle. So that brings us back to our original point. All right. Okay, moving on. Example 2. Graph quadrilateral RSTU with vertices, and it gives us all 4 vertices and its image after a 270-degree rotation about the origin. Notice it didn't give us a direction. It just said 270. So since it doesn't give us a direction, this is automatically going to be a counterclockwise rotation. Now, if you use the properties from the previous one, we have the original X and Y values are going to switch. The original X value becomes negative. So on here, do I really have to graph this whole thing? No. Truthfully, if I wanted to, I could go up to these points right now, just with what I know, and I could say, all right, we had to switch these points. So I have 1, 3, and the original X value is negative. So that's the 3 was the original X, and that's my point for R prime. For S, again, switch them around, 1, 5. The original X value is 5, so that's a negative. This is S prime. Then for T, we have, again, switch them around at -3, 5. The original X value becomes negative, so that's a -5. And again, that's T prime. And then again, the last one, switch them around, -1, 2. The original X value becomes negative, so that's -2. And this will be U prime. Now, this did not give us an example of a negative X value to start off with. If the original X value was negative, then it would become a positive. Again, that negative in our property is telling us we're changing the sign. So if it would start off as positive, it's going to become negative. If it was negative, it'll become positive. Now notice, I didn't draw a single graph yet. We're able to find those points without doing the graph. But again, we're going to show it with the graph so that you can see all the steps. But if you know the rules, you don't have to actually use the graph. Now, if you want to, you can draw this on a graph. So let's, oh, they did theirs without graphing it, just like I did. Now, on a graph, there's our points. Now, on your paper, what I recommend, using your textbook or paper, graph this. Once you have it graphed, actually take your paper and rotate the entire paper 270 degrees. So what does that mean? That means take your paper. If it originally starts off, let's see if I can use my hands to do this. Yeah, reverse it because you're facing the opposite direction. So if this is the original paper, we're going to take it, we're going to rotate it once, twice, 3 times. All right, so again, if you just do 90 degrees at a time, you're rotating it 3 times counterclockwise to do a total of 270. And if you look at the diagram and read the graph in the direction it now faces, you'll see where those points are. So when all else fails, draw a diagram and actually physically rotate that paper. All right, let's go on to the next one. All right, so on here, they're showing where those points ended up. And again, it's right here. And it's hard to tell when looking at this diagram that that's actually been a rotation around the origin. But again, it is. All right, so if you drew it on a piece of paper, you could rotate that piece of paper and it'd be easier to see. All right, so on the next thing. Oops. Clear. All right, rotation postulate. Just like the other 3, and I mentioned this earlier, or sorry, just like the other 2, I mentioned it earlier, that a rotation is a rigid motion. So just like the other ones, we can call it a rigid motion, we can call it isometry, we can call it a congruence transformation. Again, all that means is that the 2 diagrams are the same. They have equal measures, they have equal lengths for all the parts. The 2 figures themselves are congruent. So all 6 parts there, all 3 angles, all 3 sides are the same. They appear in the same order. So again, the figures are congruent. All right. On this one, performing a composition. So graph RS with endpoints, and it gives us 2 points, and its image after a composition. So we are doing a composition of transformations, just like we did in the last 2 sections. but now we're adding in a rotation. So this time they're having us do a reflection followed by a rotation. So first thing we're going to do is plot the points. So on here, we got the graph of RS, label each endpoint. And then we're going to do the first transformation, which was our reflection. And it's a reflection in the y-axis. So if we take those points, we're going to change each of the x values to the opposite sign. So again, do you have to graph it? No, this one told us to graph it. So again, if it just wanted the points, we could use those rules from the last couple of chapters or last couple of sections in order to figure out what those points would be. So first, all the x's become positive. So R, which is at -1, 3, becomes +1, 3, -3. And then S, which was at -2, -6, will now be at +2, -6. Once we do that, we can now rotate it 90 degrees clockwise around the origin. So now this is telling us to go a different direction. Now 90 degrees clockwise is actually the same as doing 270 degrees counterclockwise. And I feel like I may have skipped this in the slides. So if we're going clockwise and we subtract the number from clockwise from 360, we'd figure out what our counterclockwise rotation is. So then you can compare it back to our properties for our counterclockwise rotation. So on here, 90 degrees clockwise is the same as 270. So what's going to happen in a 270 rotation? We're going to we're going to switch them, and we're going to change the sign of our original x value, which is now in the y position. So we're going to take r prime, we'll switch them, and then the 1 will become a negative. For s, again, switch them, and then the 2 will become a negative. So there it is. We have our 90 degrees clockwise rotation, same as a 270 counterclockwise. And again, we're just switching them and changing the sign of the original x value. And those are our 2 new points. So our final rotation, our final image for this composition of transformations has r double prime and s double prime at -3, -1, and -6, -2. All right. And then the second part of this was write a coordinate rule for the composition. So they want us to write it out. So what happened? Well, first thing we did was we did our change of sign. So we made our a negative. Then we switched them around and made that original x value negative. So what ended up actually happening, we ended up with our original xy values just switched. So it became originally AB is now BA, or if you used X and Y, it's now YX. All right. Again, if you plug them in, you can check it to see if it works. All right. Symmetry. So just like we had reflectional symmetry, we have rotational symmetry. A figure in a plane has rotational symmetry when a figure can be mapped onto itself by rotation of 180 degrees or less about the center of a figure. This point is known as the center of symmetry. Note that the rotation can be either clockwise or counterclockwise. For example, the figure below has rotational symmetry because a rotation of either 90 degrees or 180 degrees maps the figure onto itself, although a rotation of 45 degrees does not. So in this example, they're showing us that we have our original figure and our 90-degree figure and our 180-degree figure look exactly the same because the figure has been mapped onto itself after that rotation. So we can't even tell that it's turned. Again, if that happens and we're at 180 degrees or less, we are going to have rotational symmetry. So we can't consider 360-degree rotation rotational symmetry. So it's always going to be 180 degrees or less. Now, I don't think, if I remember correctly from last year, this book doesn't use the terms that most books do with rotational symmetry. And that is when you have rotational symmetry, sometimes you talk about the magnitude of the rotation or what the rotational symmetry of the figure is. And if they ask for magnitude, they're just asking for how far did you turn it. All right. Now, they could also ask for how many times or how many rotations of rotational symmetry it has. And in this case, we'd have 4 rotations. The way you figure that out is the smallest rotation that we have. So here it's 90-degree rotational symmetry, and you have it 4 times, right? So 90 degrees, and again, a total of 4 times. And again, to figure out that 4, I think I skipped that. 360 degrees divided by the 90 gives us 4. All right, I'll clear that. All right, so here we go. Identify rotational symmetry. Determine whether each polygon has rotational symmetry. If so, identify the order of rotational symmetry. So order, that's asking for how many times. So if I say order, it's how many times does it have rotational symmetry. Magnitude is the degree, the smallest degree that has rotational symmetry. So for a hexagon, we have 6 sides, 6 angles there. We can rotate that so that it's mapped onto itself 6 times. So on here, again, they drew it over here. We were able to draw in some lines here to demonstrate if we were to rotate it here, it'd have the same exact figure. If we kept rotating it, again, we'd hit that same figure a total of 6 times. So it has a order of 6. What is the magnitude of that rotation? It is 60-degree rotation. So on here, a regular hexagon has rotational symmetry because a 60-degree rotation about its center maps the hexagon onto itself. The center is the intersection of the diagonals. There are 6 rotations that map the hexagon onto itself. So the order of the rotational symmetry is 6. Right. On the other one, trapezoid. This one, no matter how you rotate that, you don't get the same figure. So on here, that one does not have rotational symmetry. So a trapezoid does not have rotational symmetry because no rotation of 180 degrees or less maps it onto itself. All right, and then that's it for these notes. So again, if you want to go back over anything, you can either replay the video or you can look in your textbook. Now, again, there's an assignment. It's on Big Ideas. Like I said earlier in the video, please try to do the assignment by using Big Ideas within Canvas. All right, I'm trying to see how the assignment grades itself. I assigned it a different way than usual. So if you go to the assignment that actually has the BI in front of it for Big Ideas, when you click on it, you'll see the assignment appear within the Canvas window itself, and it should take the grade and populate into my gradebook automatically. Again, still playing around with it a little bit to see how it works, but it looks like it worked for some people for the first assignment, but not everybody. So try doing it directly from Canvas, and we'll see if that changes things. All right, have a good day.